So in example 5, we have a more complicated differential equation. T squared y double prime minus t times t plus 2y prime plus t plus 2y is equal to 0. And for the first step here, we're going to check that y1 equals t is a solution to the differential equation. And then we're going to use reduction of order to find a second independent solution. So to solve that, for part A, we're given that y1 equals t might be a solution. So if y1 is equal to t, y1 prime would be 1, and y2, or y1 double prime, derivative of 1 is 0. So we're going to plug all those into the differential equation and just see if it checks out. So we get t squared times 0 minus t times t plus 2 times y prime would be 1 plus t plus 2 times y, our y is t, and we're checking to see if that is equal to 0. And so the 0 term drops out here. So we've got minus t times t plus 2 plus t plus 2 times t, and we're checking to see if that equals 0. Now, in each term here, we've got t times t plus 2, one negative, one positive, and so it just simplifies down to 0 equals 0. So that checks. So what we did there was we just found the derivatives of this solution, the hypothetical solution that we were given, plugged them into the differential equation, plugged them in for y double prime, for y prime, for y, and simplified it down and checked that we did indeed get 0 equals 0, so it is a solution to the differential equation. That was sort of the easy part there. The harder part is going to come in part B, where we're going to use reduction of order to find a second solution to the differential equation. And let me remind you that with reduction of order, we need to have an equation of the form y double prime plus p1y prime plus p2y is equal to 0. And we don't have that yet because we have this coefficient t squared in front of the y double prime. So again, I'm going to divide that coefficient away so that we'll get the right form to invoke our formula for reduction of order. So I'll get y double prime minus t times t plus 2 over t squared y prime plus t times plus t plus 2 over t squared y is equal to 0. If I divide the right-hand side by t squared, it's just still 0. So now I've got it into this form, and so my p1, I can actually simplify that, is negative, if I cancel that t with that t squared, it's negative t plus 2 over t, and I could even simplify that some more. That's negative 1 plus 2 over t. One plus, 2 over t. So I'm going to work with that, and I'm going to use the formula that we had for reduction of order. Let me remind you what that was. We went over this in the lesson overview, but that was quite a few minutes ago, so I'll remind you what that formula was. It's y1 times w prime plus the quantity 2y1 prime plus p1 y1 times w is equal to 0. The idea here is that we don't know what w is, but we know everything else. We can fill it in and then solve a first-order differential equation for w. So I'm going to fill in everything I know. My y1 is t, so that's t times w prime plus, now, 2 times y1 prime. y1 prime is just the derivative of t, so that's 2 times 1, plus p. Okay, p1 is negative, So I'll do negative 1 plus 2 over t, and y1 is t, times w is equal to 0. So I get t w prime plus, let's simplify things in the parentheses here, 2 minus, now I'm going to distribute this t, and I'll get 2 minus t minus 2 over t times t, so minus 2. All this times w is equal to 0. I can simplify things still further. tw prime plus, now the 2's cancel, and I'll just get minus tw is equal to 0. And I can divide by t. I'll get w prime minus w is equal to 0. I'm going to write w prime as dw by dt. And maybe bring the w over to the other side, equals w. And now I'll multiply and divide. I'm separating the variables here. I'm setting up a separable differential equation. So again, if you don't remember exactly how to solve a separable differential equation, you might check back. There's an earlier lecture here on Educator in the differential equations series, and you'll see one titled Separable Differential Equations. So you can look that up and practice some examples of these if this is a little fuzzy for you. So if I multiply both sides by dt, I'll get dt on the right. On the left, if I divide by w, dw over w. So I separated. I got all the t's on one side, all the w's on the other. Take the integral of both sides. Get natural log of w is equal to the integral of dt is just t. So w is equal to e to the t. And remember, from there, we try to find v, which is the integral of w, which is the integral of e to the t dt, which in this case is just e to the t itself. And finally, our y2, remember, is v times y1. That's always the formula. You can look that up in the lesson overview at the beginning of this lecture. So v times y1 is e to the t times t, and I'll write that a little nicer as t e to the t. So that is our second solution to the differential equation. So we're done with that example, but let me recap and just remind you how all the steps worked out there. First thing we had to do was make it fit our generic form to use reduction of order, and since there's nothing in front of y double prime in the generic form, that meant we had to get rid of this coefficient of the y double prime here. So we got rid of it by dividing it away, which is where we got that t squared in the denominator here and here. And that simplified a little bit. Our p1, remember you have to include the negative sign. The t and t squared canceled down to just t in the denominator. And then it simplifies a little more into minus 1 plus 2 over t. And then we invoked this generic formula for reduction of order. You always use this formula. y1w prime plus 2y1 prime plus p1y1 times w is equal to 0. Plug in what y1 is. Remember, that was given to us. Plug in what y1 prime is. That's 1. Plug in the p1 we just figured out. Simplify it down. We get to a fairly easy separable differential equation for w. Solve that for w. We get w. And then to get v, you have to integrate w. So in this case, integrating e to the t doesn't actually change anything. So v is also e to the t. And then finally, to get your second solution, you take that v and you multiply by y1. So our y1 was t. That came from here. And so finally, y2 is just t e to the t. So that's the second solution to our differential equation here. We use reduction of order to start with one given solution and find the second solution. So that's the end of our lecture on repeated roots and reduction of order. Really appreciate your watching. This is the Differential Equations lecture series, and I'm Will Murray for Educator.com. Thanks.